Hello everybody, this is Walter and this is going to be an atypical long video. And the reason for that is because as the title says, we are going to talk and think in blockchain terms. So for some of the most seasoned software engineers that already have experience in blockchain, this will be a group of pretty basic concepts perhaps, but even if you have been developing in blockchain, you may still have some doubts about how to architect the data. And that is what I'm going to focus the most on this video. So I will be talking about what are smart contracts, how the data gets computed in the smart contract, how you model things in a smart contract, and the different kinds of data that you can use, such as deterministic and non-deterministic inputs for computing, but also some patterns around how to handle IDs and how to handle the componentization of your solution and how to make some design decisions around all of these topics. So again, I may be talking about some basic concepts, but I don't think that this is a bad idea to refresh some of them if you already have experience. So let's talk about the smart contracts. The first thing that I usually like to tell people when they are just listening about the smart contracts for the first time is that smart contracts are not smart and are not contracts. In this video, I'm going to be focusing on Hyperledger Fabric through Convector, but most of my comments will apply to most of the blockchain networks and blockchain technologies. And the reason why I am making this comment about that the smart contracts are not smart and are not contracts, it's because everybody or a lot of people think that just because something is written in the blockchain, it is a contract, and that is not true. And the other thing is that this piece of code is not smart, it's simply code. So some platforms like Hyperledger Fabric, they call them chain code, which in my opinion makes much more sense. So let's get started. First of all, a smart contract, it's basically a code. It's a piece of code. It's usually a class, it's usually a file. In this case, since I am going to focus on Convector for this example, it is a group of controllers and it is a group of models. So controllers, and at the same time there are models like that. So basically within the smart contract you usually have logic, and the logic varies depending on what you are doing, but you typically do a few things. First of all, for your chain code or the smart contract, you take an input. That input will call a function. So in this case, let's put in here a name of function. Let's say that this function is called create. It is exposed from this file that I have in here, which may be one controller or multiple, but for the sake of simplicity, let's think about just one class that has one controller. So the input gets to the function. Within the function, and let's say that all this rectangle is a function, you can do multiple things. You can do things, for example, like extracting data from the ledger. You can do some other things like, for example, validating the data that was input into the function. You can do some other things like transforming the data. And potentially, you could also as well save some data. In the middle of this different kind of tasks that you can do obviously a combination. For example, if I get this, I could have some logic saying things like if input that value a equals 1, then I could, for example, throw an exception. If not, then I could save whatever I want. So I could do something like save data. So as you can see, this is not anything else than a typical function, which at the end, based on a logic, that may look like this within the function, you then have an output. This output that gets generated from the computing of this function is what needs to be compared to be able to reach a consensus. So the first thing is, if I already built this smart contract, if I already have this logic, how is this applied in a blockchain? So we can move to the second topic, which is computing. The way that a blockchain computes the data is one of the most important pieces of a blockchain, and it's actually what makes a blockchain different from a centralized store. So before I talk about the details of what you need to know, let me talk a little bit about what makes a blockchain unique, different from a centralized system. So typically in a centralized system, you have a database. You may have an application like a server that, based on the access, it can go to the database. It may even execute some store procedures depending on the platform, or it could simply go ahead and insert data. The thing is that typically this database gets to finality immediately. That means that if the server is calling a save function and in this case sending a model, let's say that we are saving a car, the database is going to get this and it is potentially going to accept the data without hesitation. It has no reason to doubt about the data unless you specify some logic on the store procedure, but typically if you save something because you have sufficient permissions, that is enough. So again, you get to finality immediately. The thing is that this database and how this data is governed is a problem in the business. Why? The thing is that if you and I are transacting, how can you trust me that I'm managing the data in this store correctly? In any way, you have to somehow connect to my information to be able to, for example, let's think about making a business transaction. So I don't usually access your database directly. You typically have an API in here. So I will be, let's say, in this place, you have this database, and I go and I make a transaction to the API, and then I get some data. So sure, I may get some information, but what makes me sure that you won't change the value inside of your database? So let's say that we had car 1, which had a name which was Volkswagen, but you could, because you are the owner of the database and you have the governance, you could tomorrow come in here and change this to say that this is a BMW, and I will never know because I already queried the data. So this typically creates frictions because we are not on the same page, and I have simply no way to trust the data that comes to me through the API. Because once I gather the data, I have a copy of the information, and potentially on a second version, we may not be on the same page. So how a blockchain works is that it takes this model away. It brings two parties that don't typically trust each other. They get a server, which is usually called a node. Both of them agree on some rules about the computing that they are going to do. So let's put in here this smart contract. In this moment, they get a copy of the smart contract that is saved in their own node. Both of them had to sign this version. That means that cryptographically, if everything goes according to plan, they should have the same filing here with the same signature. So this becomes just a source code that may be saved in GitHub, but the actual version of the smart contract needs to be uploaded and instantiated within the node. So there is this valuable factor which is called the consensus. So for example, if somebody else wants to make a transaction, he needs to go and send the transaction to the first node and then send the transaction to the second node. If you remember from our smart contract, we had an input, which may be the same in this case for both of them, and then we have an output. That means that after the computing of the function is ready, I will get a response with some data. So let's say that this is the input, and now we get an output, which in this case it's going to be output A, and in this other case this is going to be output B. So the thing that happens in here is that if both of the nodes of the participants of the blockchain return the same value, this means that the smart contract executed in the same way. In that case, we both can trust that whatever data gets generated from these smart contracts is following a set of common rules, something that didn't happen in the centralized model, because if somebody else has the database, how can I be sure of how the data is managed, how the data is governed? In a blockchain, through this consensus that happens in here when this participant that is making a transaction basically computes based on the result of this smart contract executing once and executing twice, but in separate domains, in separate nodes. That means that these may be separate data centers. If the smart contracts are the same and therefore they are agreeing on how the logic of this data will be handled, this person or this company can send their data to finality, and therefore I could have a change in here that says car 1 and it's Volkswagen. So what happens in here is that if somebody tries to make a change that is not actually based on the rules of the smart contract, so let's say that this party changes their smart contract and now they have a new different version, and somebody sends another transaction to this node and this node, the answers, the outputs of these two transactions will be different because this member of the network changed the smart contract. Therefore, there is no way that a change can happen on the data without agreeing on the same rules of the blockchain. So what is different in general from the computing of a typical centralized database and a blockchain is that the smart contract gets executed multiple times in the domain, in the ownership of these separate companies, and therefore if everything goes according to plan, that means that the same rules that they agreed are the ones that execute, then changes to the data can happen, and therefore all of them can trust the data that is in here. So in the case of Convector, we propose this pattern, which is the controller and model that I was talking about earlier. Typically, when you think about something like controllers and models, you are thinking in something that abstracts a business entity, for example, a car, which may have multiple properties like a name, like a make, even a year of registration, and so on. And in this other case, the controller that we have been talking about have the rules on how this model will be governed within this blockchain network. So it will define how it is saved, how it is modified, and even how it is deleted. However, multiple models may be within the same business domain. So we may also have other models, for example, an owner, which may have things like an ID and which may have also things like a name. But also, models can be related to each other. So they could be directly embedded within the other model. So for example, car could be, in this case, a property inside of a person, or it could be simply a reference. The great thing about a blockchain is that how these two models relate to each other, it is defined in the rules of the controller. So, even if everybody has access to the data, they will have a really hard time making changes to the models if the rules do not allow them to compute the data in a certain way. The store of a blockchain usually looks like a NoSQL database, at least in the case of Hyperledger Fabric. This means that when you talk about NoSQL databases, you don't have tables, you just have a big store of data. Inside of the big store of data, you have a value that usually is referred through a key. So it's usually a key and has a value, and the value could be, for example, a JSON. So everything that you save, remember we have two models. These two are separate classes, separate structures. So if I save something through the controller, data will be put inside of this single store. So for example, if I come in here and I try to input a new car and it's sent to the smart contract, then this will be saved in here. Let's say that this has the ID 1. But what happens if somebody else wants to save another one? Let's say another car. This car also needs a unique ID, and this unique ID will be then saved in the same store. But if for some reason somebody tries to save this as the same ID as the first one, let's say that somebody puts that this ID has the first one, this will erase the previous value, at least for the final version of the data. In a blockchain, you have every transaction that has been computed is linked in blocks in a historical manner. I won't get into much details, but at least for the latest computed version, which is usually referred to as the world state, so the final version of the data, this will replace the first model. And this will actually happen the same if somebody comes in here and tries to save a person, in this case through another function, because the first function was for cars, and they put the same ID. If they again put the ID 1, it will overwrite whatever was in here. And why is that? It is because this store is based on a key and value, and the key has to be unique for every single model. So as long as we don't collide on IDs, we won't have a problem. And I will talk a little bit more about the patterns about data in this same video. But what you need to know is that every different model gets saved on the same store of data, but the rules that define what is what are based on the controller. So for example, in Convector, we typically add a default property which is called type, but this type is nothing but a simple property within the JSON. So this helps for doing things like indexing the data and for validations, but for you to avoid overwriting things, at least for now, you have to make some validations. If you remember, when I was talking a few minutes ago about what you add in the smart contract, you can do things like retrieving data and making validations. So you could do something like get one based on the ID, and if the result exists, then you can throw an error because you don't want things to collide and you don't want to overwrite one of your models. So that is the kind of rules that get computed independently through and are defined to or approved to be actually executed on top of the ledger based on the consensus of the computing of everybody running this same copy of the rules. So going back to what we previously named as the computing piece of thinking in blockchain about how smart contracts are executed, in this case in separate nodes, and should reach to the same conclusion to be able to save data in the store. let's talk about what kind of data can be included in the node to be able to compute. So let's explore the input that needs to be sent, in this case, by this actor in here. So let's say that this member is sending some data through an input. So he should expect to pass the parameters, which are typically either atomic values like text or numbers, or this could actually be a complex model like a JSON, for example. These parameters will reach the smart contract. They will execute on some rules like the validations that we saw earlier. Let's say that it does some validations and then it does some save of data, but also need to do some extraction of information. So like we defined earlier, we had owners and we had cars. So it makes sense that this smart contract actually will go to their version of the ledger, which in the model, for simplicity, in this diagram, I put it like this is just one database, quotes, because this is not an actual database, this is just a data store, but let's call it a database. So this database is not actually one thing, it's actually the result, the virtual result of the consensus between what these two nodes actually have locally in the node. This is what is usually called the ledger, and this other one that I have in here, it is not actually a thing, it is the result of these two having the same data. So in this case, going back to the smart contract, it gets a parameter through an input, it will compute some things, it may go and query some data from the store, and if everybody that executes this smart contract has the same data on their stores, on their copies of the ledger, it's most probably that the result of the computing will be the same, and therefore we can reach to consensus and get to finality with the data that we are proposing in the blockchain. However, what happens if, for example, this data actually, or this computing actually needs something different? This may need some extra data, some external data. So let's say that there is a web service somewhere in the internet and the smart contract actually tries to go there and get some information from the external world. In this case, since this smart contract executes multiple times and they have to go and make two queries to the same store or to the same API, they may get different values because there's simply no way to make sure that the web service is going to return the same value. So in this case, I have already talked about deterministic and non-deterministic data sources for computing in a smart contract. So the first one that is deterministic are the parameters. So the parameters that I already show in here within the input are deterministic. Why? Because those are sent from the same source of data, which is the actor that is proposing the transaction. Those are actually embedded within the parameter that was sent or the parameters that were sent from the input when requesting to execute a transaction. Another thing that is also deterministic is existing data in the ledger. That is also something that we can rely on to compute. However, the data that comes from the web service is non-deterministic. And why is that? As I was telling you, the results that come from the web service, from the external web service, may not respond the same result to every member of the blockchain. Right now, it doesn't seem like a big problem because we only have 2 members, but remember that a blockchain network is valuable based on the amount of participants that are transacting and the data that they can bring to the network. So we typically try to avoid using non-deterministic data because if in the future somebody tries to read all the ledger and see all the history of every transaction that has been executed, and they find that the smart contract actually goes to a web service and they try to recompute everything 1 year after the first transaction happened, what happens if this web service does not exist anymore? That is an example of non-deterministic computing. So we need to have always the same data for every node to be able to reach to the same conclusion about the output and therefore reach finality on the transaction. This challenge of needing external data is actually solved through a concept or a pattern that is called oracles. I won't get into much details. Probably later I will create a new video about oracles, but for now I am putting a comment in the description section of the video so that you can learn more about oracles and how you can bring data from the outside to the inside of the chain and compute some information based on on-demand data from APIs or centralized databases. By now, you already are thinking in blockchain. And why is that? Instead of thinking of a centralized computing place, you are thinking of logic that is wrapped into this concept of smart contracts that gets computed and executed multiple times inside of multiple nodes. This usually looks like a virtual machine or a container that executes the logic and securely responds to the node. And this is usually one-on-one relationship. And the second concept that you are thinking as well is about how we get to finality on the proposals of the data. But there are some other concepts that you already have that are pretty important, just like the deterministic and non-deterministic data sources for computing the data and why that is important. And I will cover a few more topics for this video about some patterns within the blockchain space. But for now, you can be sure that you have some of the most fundamental concepts about how to build with blockchain, which is great as a starting point, or if you were able to refresh some of your concepts, that is also great. So if you were paying attention, you remember that I talked about the latest version of the data in the ledger, but also I talk about some historical data. So basically, every time that a new transaction happens in the blockchain, let's say that something like this happens, we compute and we call create, and we create a car. This will be stored in the what is called in Hyperledger Fabric as the world state, which is no more than the result of what is in the ledger. So let's give this a try and see how these two stores react to each other. So we call create car from the outside of the smart contract, and in the ledger a new car is created. Therefore, in the world state, there is a car that also gets reflected. Usually, the world state is a NoSQL database in which you can perform some transactions that are usually just read-only, because the world state is simply a dependency of the ledger. That means that by itself, it is not the blockchain. It is just the results of the latest versions of the data that is within the ledger. So for example, if I create a second car, in this case, let's call it car 2, it will reflect the car 2. But if I make a change and I do something like update car 1, then in this case, in the ledger, there will be another record that says car 1, but a new version which will be version 2, and the first one will be version 1. But in the world state, nothing changed. The main difference is that what it is going to reflect is actually the data of the latest version within the ledger. So the ledger keeps track of every version of the same data, of the same object or the same ID. However, the world state only has the latest version of the information. Why is this relevant? The main reason why this is relevant is because of how you store data within the blockchain. For example, you may go and you may try to create a new car. Let's say that this is called car. This is an actual data within the blockchain. So this is called car 1. and the car has this property which is the owner of the car. So let's say that we want this car to always reflect who is the person owning the car, right? So this may be like an ID, like a government ID or something of the kind. However, what happens when you need to keep track of all the owners that this car has had? For example, because it was transferred between two different persons. So it's actor 1 and actor 2 that are transacting with the same data. So let's call this guy actor 1 and this other guy actor 2. So you could simply reflect the same value that is called, or the same property that is called owner, to say no, now the owner is the actor 2 instead of the actor 1. But this is not complying with our requirement, which was we want to know that every time that a transfer happens between this or with this car, we need to know who was the historical owner. This is really common in traceability projects in blockchain. So there are two ways of doing that. So let's drill down a little bit in the model that is car 1. So for this model, we have the car, which is the class, and we will have a property which initially is called owner. Some things that you may think about is, well, what if I, instead of putting just one owner, I do something like current owner and I add something that is called historical owners. But in this case, this second property, it is an array. And therefore, in my smart contract, remember the functions within the controller, I make sure that every time a transfer happens, I take the first or the current owner, I push it within the array that has these historical owners, and I update the current owner. So I will have something like this, current owner equals actor 2, and historical owners will have actor 1. And then if this gets transferred again, then probably I will have something like actor 3 and then actor 2. This works, right? And it looks fine. The thing is that you are overriding or the same model to put an array of the list of every owner when there are some other patterns for this. So I need to stress this out. Those are two separate approaches. It doesn't mean that the first one is better than the second one. It only means that there are two different ways and that for your requirements you need to evaluate which one is better. In this case, if you remember that we had two kinds of storage, which is the ledger but also the world state, let's reflect those two again into this example. So the first transfer transaction that happens will have this model in the ledger and this model also in the world state. For the second one, we will now have this one in here, but the world state will just erase the previous version and it will have this other version, which is the latest one computed from the ledger. So far so good, right? So it makes sense because if I'm going to make a query, let's say that I'm a user and I want to make a request to see all the owners of the car, I can simply go to the world state, which is exposed as an HTTP endpoint, or it could go through the smart contract as a query transaction, and I will have everything that I need. I know who is the current owner and I know all the historical owners. But what happens if this transfer is something that actually happens a lot? And that usually is the case of tokens. A token, since these are typically pretty liquid assets that you put in the blockchain, may be transferred 1,000 or 1,000,000 times. It doesn't matter. It will be transferred a lot of times. So creating this array is going to be really heavy because this same model will have all the history of all the owners. So this is the first pattern on how to save, in this case, or keep track of historical data for, in this example, the transfer of an asset that is a car. But there is another way. Again, this doesn't mean that this is better. This means that there is simply another way. Let's get back to the ledger and the world state to compute a little bit on here. Let's say that in this case, we don't actually want to have this model that we were showing with the historical owner. We only want to have a property, a unique property, which is the current owner. So if the first time that a model gets created, it saves the car with the owner number 1, so it will have something like owner number 1, and therefore the world state will have this data. Then the first transfer happens. We go in here, and now this will have an owner 2, and therefore the world state will only reflect the latest version of the data. But now it gets transferred again, and now it will have the owner tree, and therefore this link will have to reference and refresh based on the latest version. In this case, we only have one current owner, but we can leverage some of the features that Hyperledger Fabric has and that Convector exposes, which is querying historical data. So if you go directly and you query the world state, you will not have an idea on who were the previous owners. But if you go through the smart contract to make a query, you could simply query the ledger directly instead of querying the world state. So not the latest version, but all historical versions. So in a query, you could go ahead and call the latest version that comes from the world state, but also you may have a property that is called historical transfers, in which you will have every owner that this model had into an array. This data is not actually within the model that you have in the world state. It is coming from the historical versions. So if you have an asset that gets transferred 1,000 times, you can make the call as expensive as it is in a blockchain to get all the history of the ownership of this asset without actually impacting the storage and the computing of the typical use case, which is only knowing the current user and not necessarily all the historical owners. So you can have the same result as you can see from the previous one, but the data was stored pretty differently. Instead of always being on front, it will be based on the ledger, since the ledger is deterministic and is also immutable in most cases. You can rely on that historical change of this model to gather the data. This is one of the typical decisions that you have to make about how to compute data in the blockchain. So I wanted to give you a little bit of background on how to do this and a few examples for you to be able to make better decisions. I want to talk about one small pattern that usually we use when we architect data. The first one is that we can leave this aside and go to the store of the data. So if you remember, when we were talking about how we store the data and the IDs, I told you that if every model, even if they are with separate classes and separate types, they use the same store and therefore the same IDs will coexist within the same computing environment. So some patterns that you can apply in here is actually adding the type to the ID of the model. So instead of having a type and an ID that is only one, you may have something that is called com.cursivo.car and the ID 1. In this case, with this, you can prevent a lot of the potential issues that may arise from repeating the same IDs, because the same ID 1 may exist for a car, but may also exist for a person. So if you remember, we had this second model, which was actually a person, but the type was different. Therefore, if I am saving this as an ID 1, they won't collide because the keys are different. In this case, if we compare this with this one, those are different. So this is a typical pattern that you can apply in no relational databases. And since the blockchain store is kind of a similar logic with this key value pattern, then you can replicate that. Something else that you could have in a blockchain network is also having components that are separate but that coexist. So you may have one controller, which is a controller specifically for cars, and you may have another controller that could be specific for owners. These two controllers could be packaged inside of the same smart contract, inside of the same chain code. Let's call this smart contract 1. And both of them can compute connected to the same store of data. So while you are coding, you have two different classes, but those get packaged into the same group, into the same smart contract, and therefore they can share the same store of data. So instead of having all the code that concerns, in this case, the owners and also the cars, you can separate these and you can have one team working on the cars and one team working on the owners. Another pattern that may happen is actually having two separate smart contracts. So to separate the smart contracts, in this case, we'll have two separate contexts. So let's say that we have a smart contract 1 and we also have a smart contract 2. Let's make this a little bit smaller because this is only going to compute things related to cars, and we will have then another different smart contract which is going to be called smart contract 2, and this will only have data about owners. In this case, all the data that gets saved about the cars will be stored in this same store. But let's take this and point this to the right direction, and therefore persons will not belong in here. The second one therefore can have its own store of data, and we can architect the data separately and differently. In this case, those are two separate smart contracts, and they could also even make what we call cross-chain code communications. So this means that cars can call the logic of the owners and the owners can call the logic of the cars, but they will need to be within the same context. In Hyperledger Fabric, this means the ledger, and have the same consensus policies to avoid conflicts. So this is another pattern. It doesn't mean that one is better than the other. The first one is having everything in a single controller. This means in the same class. The other one is having two separate controllers, two separate classes for every single concept. And the other one is having two separate smart contracts that talk to each other but have separate databases, separate stores of data. You can pick the one that makes the most of the sense for your use case, but again, it doesn't mean that one is better than the other. So congratulations, thanks for holding until the end of this long video. You are officially now thinking in blockchain. So make sure that you can come back to this video and refresh the concepts if you find yourself confused. I know that a lot of people starting with blockchain are also building other kind of systems, and the way that we architect our minds around the concepts, it's completely different. So I hope that you learned something new, and if you did, please share this video with a colleague that is trying to understand what is blockchain. Thank you.